Today's quantum computers have limited qubits, we already heard that, limited fidelity and also limited coherence. The next talk will describe tools and platforms that allow companies to maximize the utility from today's computers, but also how to prepare for the computers of tomorrow. So we have Minerbi here, co-founder and CEO of Classiq, and I'm really excited to hear from him about this topic. Welcome to you. The stage is yours.
Thank you very much, and thank you for the kind invitation. So I'll share a presentation and we can start. I hope you see it now, but if not, so let me know. So as you said, we are going to speak about quantum computing software. And by the end of this talk, I want all of us to understand how can we use technology first to design the state-of-the-art quantum circuits, for quantum software for the near term, for 12 qubits, for 20 qubits, for 50 qubits, for 100 qubits, but also how to design large-scale optimized quantum circuits for a few thousand qubits. And this is the essence of what we are going to discuss. So first, I'll present Classiq. So Classiq is a quantum computing software company. We are based in Israel and in the US, soon in Germany as well. We raised over $50 billion, and we employ currently a team of 45 quantum software engineers that develop a quantum algorithm design platform that is used by enterprises and academia in order to develop software for quantum computers in an agnostic and optimized way. Among our investors, some of the global leaders in different industries, as HPE, NTT, HSBC, Sumitomo Corporation, Samsung, and of course Intesa San Paolo in Italy. And as a software company, we are partnering with all of the leading hardware providers and quantum clouds, because it is important for us to enable our users to be as agnostic as possible, right? On the one hand, you do need to specify the optimization for different machines, but on the other hand, it's important today, before we know who is the winner in regards to hardware, to develop the software in an agnostic way. So when we think about the quantum computing revolution, obviously it is about hardware and about software. From the hardware point of view, the progress is very good, right? There are different modalities, different ways to design these computers, and we don't have a clear winner yet, but we do see great progress in all fronts. We see more qubits with better quality, and we have very good reasons to be optimistic that in the next few years, we'll be able to run large circuits and hopefully gain quantum advantage. And this connects us to the second part of this revolution of the last few years, and this is software and enterprise adoption. And we do see more and more enterprises in various fields, and definitely Germany is probably the world leader in enterprise adoption, jointly with Japan, I would say. So basically, we see enterprises in various fields, in finance, in automotive, in pharma, in logistics, cyber, and so on, establishing quantum computing teams that are trying to locate the right use cases and to develop software for these machines. So of course, the use cases are very different, right? But the challenges are similar. So, we are all exploring today small machines. We design circuits for 5 qubits, for 12 qubits. We simulate circuits for 40 qubits, up to 40 qubits. But what we really want to do is to be prepared for advantage, be prepared for tomorrow's machines with hundreds and thousands of qubits. And it would be a fair question to ask, are we ready for it? And the answer would be probably no. We can't design these circuits using today's tools and platforms, because everyone who started exploring quantum software and quantum computing knows very well that this is reasonable to design, with existing programming languages, small circuit, toy circuit for 5, 6, 7 qubits. It's very, very challenging to design circuits for a few dozen qubits. And it's practically impossible to design a large-scale circuit. So this is one significant problem, gate-level design and the lack of abstraction. And the other problem is that even if you know how to design circuits for 12 or 12 or 25 qubits today, you are far from being optimized, and you can probably, using technology, get much better results. And so I'm going to discuss these two aspects. First, scaling, and the second, achieving state-of-the-art results for today's machines. But before, I want to start with one example, right? So basically, one of the most iconic and useful quantum algorithms is the Brover search algorithm, right? And basically, as software developers, what we need to do there is to define the oracle, what classical functionality we want to embed in the quantum circuit. So in this example, on 3 qubits, basically, the oracle is very simple, right? We want to mark 2 states out of 8, and definitely this could be hand-coded. But what if we want to design a more complex oracle? Still very simple, by the way, but more complex. So here we define 3 quantum registers, A, B, C, and we want them to apply to this arithmetic expression, to this arithmetic functionality, A plus B plus C and 15, so on, equals 4. So take a moment to think, how would you implement this? Okay, time is up. So let me show you how it looks like. So this circuit was synthesized by the Classiq platform. It took it like 3 seconds probably. And what you see here is quite a complex circuit. Not a large one, only on 22 qubits, but basically what you see here, so each block is a function. Inside you get more functions, and eventually when you open them all, you get a complex gate level circuit that it wouldn't make a lot of sense to design it at the gate level. So this is a problem we are solving. We want to abstract the quantum software development and to use technology in order to get the most optimized, compact results. And if I need to summarize in one sentence what we do, so Classiq synthesizes gate-level circuits from high-level functional models, enabling the design of state-of-the-art quantum circuits. So before diving into the solution, I'd like to explain where we took our inspiration from. So basically what we are solving here is a complex design challenge, right? The challenge of designing useful quantum circuits. And when doing so, we took the inspiration from another complex design challenge that was already solved. And this is chip design. So what you see here, this is an electronic circuit, not a very complex one, but yet you wouldn't like to design it at the gate level, right? And you don't need to, because in the classical world, we have high-level modeling languages like VHDL, like Verilog, and synthesis tools like Cadence and Synopsys, which basically allow us to define a functional model of the circuit. I mean, what functionality we want to achieve, but forget about implementation. Implementation is done by automation. So this is what our technology does. The Classiq platform enables the user to define a high-level functional model of the circuit. This is kind of VHDL for quantum, but the gate-level implementation is then automated by the synthesis engine. So what a user needs to define is what functionality he or she wants to achieve. In this case, this is the Brover oracle, like in the example before. So this is the expression you would like to embed in a quantum circuit, and also what are the constraints. So you want it to work on maximum 12 qubits, and you want the output format to be Q-sharp in this case. And then the synthesis engine is exploring the entire design space and choosing a circuit that first meets the user's demands and constraints, and second is optimized. So when you take a look at a quantum stack, this is how it looks like. So basically, the user defines the functional model and constraints, which are important, right? Because on the one hand, you can be hardware agnostic. You can just define functionality, and you can get the circuit with any optimization criteria you want, minimal number of gates or minimal number of qubits and so on. But if you do know on which hardware you are going to run it, so it's very helpful to embed hardware-specific constraints like connectivity, like noise model, like preferred gate set, and so on. And then the synthesis engine is exploring the design space, and it generates for you the circuit in any output language you choose. So we are already deeply integrated with the IBM, Microsoft, Google, Amazon, IonQ solutions. So basically you can just choose. It could be Qiskit, OpenQASM, QIR, Q-sharp, Cirq, Ticket also. And then this circuit is compiled and sent to run on the cloud, the quantum cloud of your choice. So why is it good for? It's good for first being able to build sophisticated quantum circuits in a scalable way, right? When you define the functional model, so you don't really care if it should be designed on 12 qubits or 1200 qubits. For you, it's the same. Automation is doing the hard work. Also, it reduces by orders of magnitude the required resources. And I'm going to show it in a few minutes how using the modeling and synthesis saves a lot of resources comparing using only transpiler or compiler. And it dramatically reduces the development time, right? For two reasons. First, because it's much easier to define functionality, but not gate level implementation. But the other point is when you divide the functionality and the hardware constraints, so you can define the functional model once, and then you don't need to tailor-made different circuits for different machines. This is done by automation. So this is another aspect. And of course, embed domain experts, which are non-quantum experts, to the flow. Quantum experts are very important, and probably the most sophisticated functions will be developed by them. But using these functions in order to build sophisticated models, this is something that our customers are definitely doing with no quantum expertise, but with domain expertise, of course. So I want to show two examples. First example is going to show how this technology is scalable, how with a simple model we can design very complex circuits. And the other one will show how we can use this technology in order to get state-of-the-art results, even on small circuits. So this industrial use case designed by one of our customers is the 3-SAT or K-SAT optimization solver, in this case for formal verification. It could be also for more optimization use cases. So basically what you see here, this is the model. So first you need to define the functional model. In this case, these are the constraints. These are the 3-SAT constraints that the user wants to fulfill. Then you define the constraints. In this case, up to 13 qubits and maximal depth of 5,000. And then you define the backend of your choice. In this case, that is the Qiskit simulator, but it could be Azure Quantum or Bracket or any other backend. And then you get different circuits. You get different circuits for different optimization criteria. And the interesting thing here is that all of these circuits have the same functionality. So with the same functionality, circuit 1 is optimized for circuit depths. It uses 13 qubits, but it's very shallow. Circuit 2, on the other hand, is more deep, but it uses only 8 qubits. And the third one is optimized for overall accuracy. So it uses 12 qubits with, average depth. But then it could be much more complex, right? We could ask for a much more complex 4-SAT optimization problem. And then if I take a look at the circuit that was generated, you can see, I hope you can see, that this is quite complex, right? And it was synthesized by the platform in few seconds, and it would have taken months for a person to design at the gate level. So I'll return to the presentation and give one more example. So now what we saw is how to abstract your way into very complex quantum circuits. But part of our users are very interested in optimizing small circuits for today's machines, right? So what we show here is that even for these circuits, we get a much better optimization. So in this case, this is the H2O Hamiltonian simulation, and this is only on 12 qubits. But the beautiful thing is that when you use this, when you allow the synthesis engine to optimize, and after that you transpile and compile, so you can save over 50% of the gates, of the number of CNOT gates, than only using transpilation and compilation. So I don't want to take extra time. So basically our users are first using a pre-built model in application suites, in finance, in chemistry, in QML optimization, and also they create custom functions and more complex models and run them on various machines. There are a few examples here in finance, in QAOA, and this is also used in academia. This is a course in Carnegie Mellon University that uses the Classiq platform for quantum education. And I would love to answer any questions now or in offline if we don't have the time. And thank you very much.
Thank you, Mr. Minerbi, for the very interesting insight. I think it's particularly relevant in how many industries quantum computing can become relevant. So thank you also for providing us with the use case already. I think making the connection between what's the technology and how to translate that into business value is always a big challenge, and we'd like to continue with that